We will now have our research presentation, again introduced by Interim Vice President for Research and Innovation, Doug Gage.
Thank you. As we celebrate the success of our graduates and the completion of another academic year, it's also our tradition to highlight exceptional student research during the April Board of Trustees meeting. Our research speaker today is Sneha Benerjee. She is a PhD candidate in electrical and computer engineering in the College of Engineering. Sneha received her Bachelor of Science degree in electronics and communication engineering from West Bengal University of Technology in India. And in 2012, a Master of Science in Radio Physics and Electronics at the University of Calcutta, also in India. Her current research interest includes quantum tunneling in metal-insulator-metal junctions, electronic emission, and contact engineering. And before your eyes glaze over, let me tell you that Sneha is a great storyteller, and you will understand that by the time she's finished. She is a recipient of Michigan Institute of Plasma Science and Engineering Graduate Fellowship Award in 2020 and 2021, the 2020 MIPSE Graduate Student Symposium Best Presentation Award, and in that same period, Michigan State University's Electrical Engineering Outstanding Graduate Student Award, and the 2021 IEEE Nuclear and Plasma Sciences Society Graduate Student Award. Sneha is also the founder of the IEEE Nuclear and Plasma Sciences Society Student Chapter at Michigan State University, which was founded in February of 2020, and she's served as its president since its founding. Please welcome Sneha Benerjee.
Thank you, Dr. Gage, for the kind introduction. Can you all hear me and see my screen? Okay.
Yes.
Good morning, everyone. I'm Sneha Benerjee from Electrical Engineering Department. I work with Professor Peng Zhang, and today I'm going to present our work, modeling of nanoscale electrical contacts. I'd like to mention that this is a huge honor for me to present our work in front of you in this meeting today. So thank you for giving me this opportunity. Nano means small. How small exactly? Well, 1 nanometer is 1/1,000,000th of a meter. 1 nanometer is about as long as your fingernails grow in 1 second. One strand of your DNA is 2.5 nanometers wide. And the villain of this century, our invisible enemy, coronavirus, is about 50 to 200 nanometers wide. Electrical contacts in such small scale are the building blocks of next generation electronics, where our gadgets are going to be smaller, lighter, faster, smarter, and cheaper, just like science fiction movies. Our ever-increasing demands for physical scaling down and high efficiency have pushed the electronics industry to its limits. Your smartwatch probably has millions of tiny electrical components and connections inside, which are already as small as your red blood cell or a bacteria. If the electrical circuits are scaled down further and built in the scale of nanometers, some spooky phenomena occur. Our traditional electrical theory says if two metals make perfect contact, the electrons see no barrier and they can happily flow through the circuit. So we have current. When the metals are far apart and the media between them is an insulator, like air, they cannot cross the barrier. So we do not have current. However, nanometer scale is called spooky regime because even if the metals do not touch each other, the barrier is narrow enough for the electrons to cross over. Hence, we have spooky current. This spooky current is called quantum tunneling current and is governed by the theories of quantum physics. Now, this tunneling current is a problem. Imagine you want your current to go in the X direction, but due to this leakage, now it goes in X and Y and Z direction, which can cause noise, heating issues, device malfunction, and failures. On the other hand, this tunneling phenomena can be utilized to develop some novel devices that can overcome the shortcomings of existing silicon-based electronics. The goal of my thesis is to develop mathematical models to understand, control, and improve electrical current in nanoscale contacts. First, we systematically studied the tunneling current for different contact members, input voltage, insulator barrier, and the gap distance. And then we applied that knowledge to manipulate current distribution in a practical electrical contact. One interesting thing we found is that although spooky current or tunneling current imposes some serious challenges to the circuit engineers, strategic design of such contacts can eliminate some of the long persistent contact problems present in the industry, like current crowding. Current distribution in a practical electrical contact is non-uniform. Current crowds near the edges. And this current crowding is especially severe for highly conductive ohmic contacts, which means a perfect contact between two contact members without any gap or insulator. We found that if the two contact members are separated by a thin insulating layer whose dimension is in nanometers, this current crowding effect can be eliminated. And we need to eliminate this current crowding effect because it induces non-uniform heating of the contact area, which can cause localized thermal hotspots and heating issues. And in the worst case scenario, can cause even device failure and small explosion, which are undesirable. In this figure, we plot contact current density along contact length. The black dotted line here is for ohmic contact, where no gap is present between the contact members. And the colored lines here are for tunneling type contacts, where we considered two gap distances, 1 nanometer and 3 nanometer. We see that the current distribution is more uniform when a thin in nanometer scale insulating layer is introduced between the contact members. So we make an important conclusion from this figure and our research, which is that current crowding effect, which is a major challenge in nanocircuits and electronics industry today, can be eliminated by introducing a thin nanometer scale insulating layer between the contact members. And we call this method tunneling engineering. And we cannot wait to apply our design approach to the industry, welcoming new technologies and improving upon the existing ones. Excuse me. We have 4 published and 1 unpublished, still under review journal papers on this project. We also have a US patent that was approved last year. I would like to thank my advisor, Professor Peng Zhang, for his mentorship. I would also like to thank my colleagues from the Nanopath Group of Electrical Engineering Department for their support and encouragement. This work is supported by Air Force Office of Scientific Research, Michigan Institute for Plasma Science and Engineering Fellowship, and Michigan State University's Graduate Writing Fellowship. Thank you for your attention and time. I can take any questions if you have any. And once again, I'd like to thank you for giving me this opportunity. Thank you.
Well, thank you so much, Ms. Banerjee, and what a wonderful presentation. Does anybody have questions for Ms. Banerjee? Dr. Gage was absolutely correct. You explained that in such a wonderful way that I think all of us understood what you were doing and are all very impressed. And thank you so much for taking the time to do this presentation. The work obviously seems extraordinarily important, and you really epitomize, I think, one of the important things that Michigan State is able to do, and that's to bring talented people from around the world here to study. So thank you for your contributions to the field and for choosing Michigan State to do your graduate work. We're very proud that you did, and thank you again for taking the time to do this today.
Thank you so much.
You're very
Thank you.
welcome.